Hello, friends, and welcome to another lecture on chemical engineering thermodynamics. Today, we'll be taking up a rather lengthy problem. Now, this problem has come in Mumbai University CET I question paper, okay, for 10 marks. And this has come in December 18, and the question number is 4A. Now, it asks you derive the relation to estimate the residual enthalpy and the residual entropy of Redlich Kwong gas. The Redlich Kwong equation of state is given by, and it's on your screen, and where A and B is given to you. Now, just remember one thing, that in the Redlich Kwong equation of state, there is a misprint here in the question paper. It comes as A upon V plus B, and there is a root T here too. Okay, so it is A over root T V plus B. Now, I would always advise the students to um, commit to memory these two formulas because they help a lot in solving the residual enthalpy and the residual entropy problems quickly for any equation of state that we get. Remember, as I told you earlier too, that we cannot mug up all the formulas. It's just simply impossible. And that is what even teachers try to see in the university question papers, that problems are given in such a fashion that if you mug up the formulas, you may be successful, but not everybody can be successful and be having that big of a memory, that big memory. So always try to commit a few formulas in your memory and use them to solve the problem, right? So coming back to the problem now we have here delta hr. Okay, so we have delta hr here. Now let's solve for the residual enthalpy. So it's simple here. What we need to find out is only, we have the formula here. What we need to find out is only, see what is common in these two formulas, finding out dou P by dou T at V. So let's do that first for the Redlich Kwong gas. So what we have for the Redlich Kwong gas is P is equal to RT over V minus B minus A over root of T V plus B. That's right. So we differentiate this dou P by dou T at constant volume V, right? So if we do this, we get R over V minus B minus A over V plus B, right? And this is 1 by 2 root of minus 1 by 2. So if we differentiate it, we are going to get as into minus 1 by 2 into t raised to minus 1 by 2 minus 1. So that's going to be equal to R over V minus B minus, so that becomes a plus now. So it's going to be A 2, and then we are going to have 3 by 2. So we can write it as T root of T V plus B. So we can write it down this way, and we can write dou P by dou T at V. That is what we get now, right? So let's quickly calculate the residual entropy part. So the residual entropy is now going to be equal to delta H R is equal to R T Z minus 1 and plus integral of V infinity, that is at a very low pressure, from a very, very low pressure to V at V. That's going to be equal to RT over V minus B plus A upon 2 root of T V plus B, and that's going to be further. Let's write the formula for P. So that's going to be minus P. So minus P is going to be minus RT over V minus B, and that's going to be plus A by root of T V plus B, and we have dV finally here. So we can write down as delta H R is equal to RT Z minus 1 plus integral V is equal to infinity to V is equal to V, and we have RT V minus B cancelling off, and then we have A by 2 root T and this. So this is going to be 3 by 2 A root T into 1 over V plus B dV. Right? Now, what we can do here is we can factorize 1 over V plus B. So we can factorize this off. So if we factorize this off, what we are going to get here? We are going to get, let's do it in a very systematic way. Let's remove this off. And afterwards, let us remove this integral from here. And then afterwards, integral V is equal to infinity to V. And then afterwards, we have B, which is going to be common here. And we are going to have in, after factorization, 1 minus V minus 1 over V plus B, and then we have dV, right? So we are going to have it as RT Z minus 1, and then we have plus 3 by 2. Now what do we do? Okay, so let's start solving it. Let's leave it as A root of T B. Let's leave it at that. And if we solve this integral which is inside, we are going to get ln V over ln of V plus B from V infinity to V. Okay, so I write infinity here now, right? Now, if we have to integrate this, now V infinity, if I'm going to put V infinity here, remember one thing, that 1 by infinity is going to make it 0, right? And we are going to have it as a 0 value finally after this. So we will have only V plus B remaining. The infinity part is going to go off. So we have it as RT Z minus 1 plus 3 by 2 A root T B ln, and now V plus B can be modified as such, where we can write V as ZRT by P and ZRT by P plus B. We can remove RT by B common here in this, and finally we get the formula as delta HR, that's your final expression, RT Z minus 1 plus 3 by 2 A over root T B ln z over z plus b. So this is the expression you have finally, and let's make a note of it. So that's your final expression which you're going to get for the residual enthalpy. Now, can we do something interesting here? We can define A as A P by root T R T square, and we can define B as B P by R T. So what do we get now? If we take A over B, we get A P over root T R T square B P by R T. So R T, you get it cancelled here. B and B also gets cancelled here. And we are finally left with A over root T B R T. Right? So what we can do is we can rewrite this equation in terms of A and B. If you wish to show a further modification of this equation, RT is Z minus 1 plus 3 by 2 RT A over B and ln Z over Z plus B. So this is a modification you can show and you can use also, right? So RT can be common here, and we have Z upon Z minus 1, and we have 3 by 2 AB. So it can be used conveniently whenever calculations are required. Okay, so you may have problems where you may be asked to prove what is the residual enthalpy and then solve a problem on that also. So this becomes a very convenient form to solve it. Now let's take up for the entropy. So what do we have is delta S R is equal to dou P by dou T. Okay, so RT ln Z. So let's write down RT ln Z plus integral V infinity to V, and then we need just dou P by dou T. So we have already got this here, R V minus B. So that's R V minus B plus 2A over 2T root T V plus B, right? So that's A over 2 root T into T into V plus B, right? And then what we have is the third member here is R over V, and then we have dV here. So that's pretty simple to solve now. Now delta SR is simply going to be equal to RT ln of Z. That's not RT ln of Z, that's R ln of Z. So let's remove this T out. That's R ln of Z. Okay. So there we are. There we are. That's R ln of Z. So R ln of Z. And now let's work on what is inside this bracket, right? Now what is inside this bracket is we have this expression. So this expression finally can be written as plus integral of, right? First of all, we have R here. Okay. So what we can do is we can remove R as a common factor here and try solving it. So that would be a great idea. So we remove R as a common factor out. After we remove R as a common factor out, we can write the equation as such, where we can start the bracket, and the first integral is going to be dv over v minus b, v infinity to v, right? The second one can be integral dv over v, and the third one can be plus a over 2 rt root of t, and this can be written as b here, and this can be written as now 1 by v minus 1 over v plus b dv. Okay, so that really simplifies quite neatly, and we have delta SR is equal to R ln of Z. Now let's take the first one. That's going to be plus R ln of V minus B. Okay, that's going to be the expression now. And then we are going to have V infinity, that is the lower limit of the volume. Okay, so that's it. And then we have minus R ln of V. So the lower limits are going to cancel off each other into these two equations. So we can write them as follows. So it can be written as R ln of, first we have is V minus B, V minus B. Then what we are left with is V. Then what we are left with is A. So we can do the usual modifications here as we have done in delta HR. We can write this as AP over RT square root of T, and we write 2 here and we write BP by RT, okay, into ln of V over V plus B. That's going to be your final expression, which neatly, with a lot less explanation now, because I have already said that you can easily replace V for a real gas as ZRT by P. So without showing the working of it, I will put the final expression now, which can be got very easily. R ln of Z plus R ln of Z minus B by Z, right? So we have Z plus A over 2B ln of Z over Z plus B. So this is the expression we are going to get now. And there we are. Since we knew the formula for residual enthalpy and residual entropy, we could solve this very easily, because what is common here? We only need to find out dou P by dou T, right? So this formula can be used for any cubic equation of state, that is Redlich Kwong equation of state, or Redlich Kwong equation of state, or the van der Waals equation of state. So we can easily derive out what we want. So that was all, guys. Hope you have learned something from this lecture, and do keep watching my lectures. Please subscribe my channel. My channel has low subscription. It does not have subscription of 1,000. Now this is not an enough motivation to keep continuing this way. I need more subscriptions to feel motivated to continue and help the student and the teaching community at large. So please share my videos. Please ask people who get benefit of my videos to subscribe it, and that is going to be a great amount of motivation for me. I am looking forward that the community which is watching my video takes my subscription to 1000 quickly. Currently it is 588. I request you to take my subscription to 1000 as quickly as possible. This is a request. This is a humble request. Please. Okay, friends. Goodbye. Have a great day. Have a great time.